Welcome back to an introduction to real analysis. We continue working through the text section by section. We're now in chapter 2, section 6, more on series. What are we going to do here? We're going to continue developing our understanding of series. We're going to prove some more convergence tests. We're also going to talk about power series. Now, one test we'll introduce is similar to the ratio test. It's called the root test. The proof will be very similar to that of the ratio test. And again, the idea will be to generalize what happens to geometric series through a comparison argument. So let's take a look at the root test. Suppose you have a series and let L be the lim sup of the absolute value of xn to the 1 over n, the nth root of the absolute value of xn. If this lim sup is less than 1, the series converges absolutely. If the lim sup is bigger than 1, the series diverges. And again, much like the ratio test, if this lim sup is 1, no conclusion may be drawn. All right. So let's get proving. First, we're going to assume that this lim sup is bigger than 1. Whether that means it's a real number bigger than 1 or plus infinity, simply pick some real number bigger than 1 but still less than L. So since we have a lim sup of L and R is less than L, there must be a subsequence along which we are approaching that lim sup, in other words, bigger than R. So the nkth root of the absolute value of xnk along this subsequence will be bigger than R. Simply raising both sides to the nk power, now since R was also bigger than 1, we get that the absolute value of xnk is bigger than 1. Therefore, there's a subsequence of terms of the original series for which the absolute value is bigger than 1, meaning it is not converging to 0 on this subsequence. So the terms of the sequence overall are not converging to 0. And if we have a sequence not converging to 0, the associated series is not converging. So let's move on to the situation where L is less than 1. Since we're taking a lim sup of some absolute values to the 1 over n, this lim sup is definitely not negative. Pick an R in between 1 and L. Now R is larger than the lim sup of a sequence, meaning past a certain point, every term will be less than R. And by every term, we mean the nth root of the absolute value of the original sequence, because that was what we were taking the lim sup of. So past a certain index, capital N, the absolute value of xn to the 1 over n is always less than R. In other words, the absolute value of xn is less than R to the n. Then, if we look at the nth partial sum, where we are now attempting to show absolute convergence, so we're going to take an absolute value of xk in here, we're going to break off up to index n minus 1 and then look at past index n as a separate collection of terms. So the first sum is simply a constant. Capital N is a fixed index now. Now the second series here, this absolute value of xk is less than r to the k, but remember r was between 0 and 1. So the sum of r to the k converges because it's a converging geometric series. By the comparison test, so does this series here as n goes to infinity. And this was just a constant. So the original series converges absolutely. And once again, if we look at the alternating harmonic series and the harmonic series, now the relevant lim sup, it's in fact a limit, of the absolute value of the term to 1 over n is 1. And one of these series diverges and one of them converges. So just a nice little example to show that when this lim sup is equal to 1, do not attempt to draw any conclusion. Let's look at proposition 2.6.2. This is known as the alternating series test. Suppose you have a sequence which is monotone decreasing with limit 0. Then the series given by negative 1 to the n times xn converges. So the alternating series test is phrased a little bit differently in just about every text. Here we have a sequence of positive numbers that is decreasing to 0. The series is then formed by taking that sequence and multiplying by negative 1 to the n. That's the series which we're going to say converges. Look at the proof. The sequence of xn's is monotone decreasing. Therefore, x2n minus x2n plus 1 is non-negative. Now in the series we wish to construct, observe that the index on n is equal to the power of minus 1. Here I have index 2n with a 1. Here I have index 2n plus 1 with a minus 1. 1 is negative 1 to an even power. Negative 1 is negative 1 to an odd power. So when I add two consecutive terms of the series, we wish to construct, if I add two consecutive terms of that, an even index and an odd index, that net result is not negative. So the subsequence of partial sums of the series we will eventually construct, specifically the subsequence of odd index, that is a monotone increasing subsequence. The first term is simply -1 to the first times x1. Then I add on -1 squared x2, -1 cubed x3. That raises the value. So this partial sum is less than or equal to this one, is less than or equal to now adding on x4 minus x5, and so forth. Therefore, the odd index partial sums of the series we construct are monotone increasing. So the odd index partial sums are monotone increasing. We're now going to claim that they are bounded above specifically by 0. So the odd index partial sum, given by this form here, we can write, instead of going from index 1 to 2n plus 1, we can specifically take -1 times odd index plus +1 times even index. Now k has to go from 1 to n. Note when k is equal to 1, we get a negative x1 plus x2. When k is equal to n, we get a minus x2n minus 1 plus x2n. So since this original sum here went to index 2n plus 1, the only thing that's missing is a minus x2n plus 1. Now every term in this sum here is non-positive. Remember, the original sequence is decreasing. So here I have a plus and a minus, but this is a larger index than that. So this is a smaller amount than this is. So I have a smaller amount with a plus and a larger amount with a minus. Every of these parenthetical terms is less than or equal to 0. So this sum is less than or equal to 0. And now I am subtracting x2n plus 1, and our original x's are positive. So all of these are non-positive. This is explicitly negative. So the odd index partial sum are all negative, meaning they're bounded above by 0. So every odd index partial sum is less than or equal to 0, but they were monotone increasing. So since the odd index partial sums are monotone increasing and bounded above, the odd index partial sums on their own have a limit. Now a fairly similar argument, but applied to the subsequence of partial sums of even index. First, our original sequence was monotone decreasing, so I can take this difference and get something bigger than or equal to 0, multiply by -1, and flip the inequality. Now I have -1 times an odd index term, +1 times an even index term, so we throw those powers of -1 in there. And this tells us that the partial sums of even index is monotone decreasing. When you add an odd plus the next even index term, the result can only go down. So S2 is bigger than or equal to S4, is bigger than or equal to S6, and so forth. Having established then that the even index terms are monotone decreasing, we just want to show that they're bounded below, specifically by -x1. So look at an even index partial sum. It's the previous partial sum plus the next term, and since this specifically has an even index, it is being multiplied by -1 to the 2n, which is just going to be a +1 here. Because our original sequence is made of non-negative numbers, this is bigger than or equal to s2n minus 1. But remember that the odd index partial sums we've already shown to be increasing, meaning s2n minus 1 is at least as big as s1. S1 is simply explicitly -1 to the first times x1. So S2n bigger than or equal to minus x1. So the even index partial sums are decreasing and bounded below, therefore the even index partial sums on their own have a limit. Let's draw a picture to show what we've been doing here. Here are going to be the values of x1 through x7. They are positive but decreasing. But in our series, the odd index terms are going to be made negative. So now let's construct some partial sums. First, the first partial sum is simply -x1. To get the second partial sum, I add the quantity x2. So now we have a line for the second partial sum. Next, I subtract x3, then I add x4, then I subtract x5, then I add x6, subtract x7, and so forth. So observe that our odd index partial sums can only go up, but they are bounded above by the even indexed partial sums that can only go down, which are in turn bounded below by the odd index partial sums. Okay, so the even index and odd index partial sums both have limits. Note for any particular n, the difference between two consecutive partial sums in absolute value will always be the term that was added on. Taking a limit of both sides, because we assumed our original sequence has limit 0, we find that not only do the odd index and even index partial sums have a limit, they have the same limit. I'm going to call that L. So now the even and odd index partial sums both converge to L. For any positive epsilon, past a certain point, the even index n's will have their partial sums within epsilon of L, and the odd index n's will have their partial sums within epsilon of the same L. Meaning, past a certain point, to make both of them true, every single n will have its partial sum within epsilon of L. A brief comment about speed of convergence. The alternating series test requires that the underlying sequence be converging to 0 with no conditions on how fast or slow that convergence is happening. So as a side remark, I mentioned that for any sequence of positive numbers xn converging to 0, one may construct another sequence yn converging to 0, but for which this limit is infinite, meaning xn and yn are both going to 0, but theyn's are much bigger in a sense than the xn's, meaning theyn's are converging to 0 much slower than the xn's are. So there's no such thing as a slowest possible convergence here. No matter what xn you have converging to 0, you could make another sequence converging to 0 even slower. But the alternating series test could still apply to an alternating series constructed out of that sequence. Let's now talk about rearrangements. Absolutely convergent series behave as you would hope. You can sum them up in any order you want. So nothing of the sort holds for conditionally convergent series. See, for example, the following two exercises. Consider a series, xn, and a bijective function between the naturals to themselves. So this is a rearrangement. Here, instead of summing up x1 plus x2 plus x3 and so forth, we sum up x sigma of 1 plus x sigma of 2, but this is a bijection. So we'll get all the same terms just in a different order. Changing the order in which we add terms is like attempting to derive some sort of commutative property for infinite series summation. A plus b is certainly equal to b plus a. Inductively, a1 through an can be added in any order you want. But induction applies to every natural number. It does not apply to infinite quantities. So can you rearrange an infinite collection of things being added and still hope for something to happen? So here's proposition 2.6.3. Suppose you have an absolutely convergent series, and sigma being a bijection, a rearrangement. Then the rearrangement is still absolutely convergent and converges to the same thing. So if you have an absolutely convergent series, you may rearrange it however you want without changing whether it converges or what it converges to. We can actually prove this. Let epsilon be positive. The original series is absolutely convergent, so there is a cutoff point past which this partial sum is within epsilon over 2 of the eventual limit, and the tail of absolute values is also less than epsilon over 2. These partial sums must be converging to x, and the tails must be converging to 0, so I can get both of these to be less than epsilon over 2. Okay, so there is a capital K, so that for all little n's up to capital M, there's a k less than or equal to capital K, so that sigma of k equals n. What are we saying here? Sigma is our bijection between the natural numbers. There is a cap capital K so that for every number up to n, we have seen it be spit out as sigma of something. So in your listing, sigma of 1, sigma of 2, sigma of 3, and so forth, eventually 1 is in there, and eventually 2 is in there, and eventually 3 is in there, and so forth and so forth. If you list out sigma of 1, 2, 3, 4, 5, you get a bunch of natural numbers. Eventually you see everything up to and including m. That cap on how far you have to go to see 1 through m in the range of sigma is capital K. So for each n up to m, there was a k that spit it out. You can put it like this as well. 1 through capital M appears within sigma of 1 through sigma of k. So we have 1 through m, a subset of sigma of 1 through sigma of k. Now if we take capital N past that point, let capital Q be the maximum of all of these numbers. This is just a listing of natural numbers and it's finite. Take the biggest one, call that Q. Okay, now we sum going up past this point in our rearranged version. So we will have added up all of these things plus some more terms, meaning we will have seen x1 through xm, because remember, 1 through m appear in this list. So if I add up a whole bunch of terms, including this list and beyond, we do see numbers 1 through m and then a whole bunch of other garbage. This is just x1 through xm, and this is everything else. So now subtract the limit value x. On both sides, take an absolute value. On the right-hand side, we're going to apply the triangle inequality. Here, I split it up as this plus that, triangle inequality as promised. What do we know? The original series is converging to x. However, over here, we're going to apply the triangle inequality again. This is a finite sum, so the absolute value of the sum is less than or equal to the sum of all the absolute values. So now we've established that our rearranged series compared to the limit x is no larger than some partial sum of the original series compared to x plus a whole bunch of absolute values. Now the first sum is less than epsilon over 2, but the second sum is definitely less than the sum as n goes from capital M plus 1 to n of all of these terms. Why? Here, from our listing, x sub sigma of 1 through x sub sigma of capital N, this just accounts for actual subscripts 1 through m, not sigma of 1 through sigma of m, actual subscripts 1 through m, and this was everything else. So we definitely account for everything else in that sum. We also assumed on the previous slide that we were sufficiently large in our indices so that this sum was also less than epsilon over 2. So we have an epsilon over 2 plus epsilon over 2. Therefore, our rearranged series is also converging to x. Now, if you do the same argument for not the sum of xn, but the sum of the absolute values, you'll find this also converges to the same thing. It's the same argument, just presume that the series you began with was entirely non-negative. Therefore, the absolute value does nothing and the previous proof works. So the new rearranged series is also absolutely convergent because the original series was presumed to be absolutely convergent. Let's take a look at an example. We're going to take the alternating harmonic series, and we're going to rearrange the sum to be anything we want. This is in stark contrast to the previous proposition. The previous proposition stated that an absolutely convergent series, no matter how you rearrange it, will converge to the same thing. Here we have a conditionally convergent series. We're going to show we can rearrange it to do whatever we want. So this is known as the rearrangement theorem or the Riemann rearrangement theorem. The general result is left as an exercise. We're specifically doing it for the alternating harmonic series here. So for convenience, let a sub n be the general term in our alternating harmonic series, and let L be an arbitrary real number. So note If all you did was add up 1 over the odd numbers or 1 over the even numbers, those would still be diverging. Okay, this is a minor exercise. They do require some proof, but you can do a straightforward comparison test with doing something with the harmonic series that you began with. A way to phrase this is that in our alternating sum, we have positive terms, and there's enough of them to make really big quantities, as big as you want. We have negative terms, and there's enough negative terms to be as much negativeness as you want. So the tails of these series must also diverge, meaning no matter how many positive or negative terms you have crossed out or used up, there are enough left over to make as much positive or as much negative quantity as you want. So we're going to inductively rearrange our terms so that eventually we will end up with the limit of the partial sums being L. Define n1 so that we add up a bunch of positive things to be less than or equal to L, but if I added a single additional positive term, I would exceed L. I know I can do this, remember, because the positive terms on their own diverge. So add up a bunch of them until you exactly get larger than L. So set sigma of 1 to be 1, sigma of 2 to be 3, and so forth, so that I add up exactly those terms. And then I go to be just a little bit bigger than L. Note, if L started off less than or equal to 0, just start with an empty sum here. So we're adding up enough positive terms to be just a bit bigger than the L we want. Now what? Define L1 to be the limit we wanted minus the sum we just constructed. Remember that the sum we just constructed was bigger than L, so this is definitely a negative quantity. So now I start adding negative terms until I just go past L1, to the left, just less than it. And now I set my rearrangement to start adding on these. So having previously added enough odd index terms to be just a bit bigger than L, we're now going to add just enough negative terms to be just a little bit less than L. We keep going in that manner. Having added just enough positive terms to be bigger, then we subtract enough negative terms to be lesser, then add enough positive terms to be bigger, and so forth. So we rinse and repeat that argument over and over again. Now we have constructed an injective rearrangement because we were using our odd and even terms in order. So we only use each term once. We have to keep going over and over again. Every time we do this, we use at least one odd index term and at least one even index term. So we will eventually use all of them exactly once. Okay, so we are not just injective, we are also surjective. Once we use a term, we don't use it again, but because we go back and forth infinitely many times, using them up in order, we do use every single term that we started with. So finally, as we have this sequence of partial sums that just exceed L, and then just to the left, and then just above, and so forth, by how much do we go above or below L is a single term of the sequence we started with. Okay, the last term we added is exactly moving the partial sum by the size of that quantity. So all subsequent partial sums are that close to L. We just barely went above L, then just barely went below it, and now we start going up. So I never go below that quantity again, and then I never go above, and I never go below, and so forth. So as close as we get to L at any particular step, we then stay that close. So having barely been larger or barely been lesser than L, we now change direction and start moving in the opposite direction to only get closer. And the alternating harmonic series that we began with is convergent, so the individual term has to converge to 0, meaning the amount by which we move at every step is converging to 0. So as we change direction and go up and then down and then up and then down, we always miss our target by no more than the size of one term, meaning the amount by which we are off is converging to 0. The distance between our partial sums to L is converging to 0. We've been a little squishy on the details here, and transitioned more to a sort of written argument. As I mentioned, the general result is left as an exercise. Let's talk about how to multiply series together. We've already mentioned that multiplication of series is a bit harder than adding. If one of the series converges absolutely, then the following theorem, 2.6.5, is called Mertens' theorem. We'll prove it shortly. For this result, it will be convenient to start at index 0 rather than 1. So here is the statement of Mertens' theorem. Suppose an and bn are convergent series converging to a and b respectively, and suppose the first one is converging absolutely. I define Cn to be these partial sums where the index on A is increasing from 0 to n, while the index on B is decreasing from n to 0. Then the series made up of these C's converges to the product A times B. All right, let's prove it. So Cn is exactly constructed to have all products of an A with a B where the sum of the index is n. Whatever the index on A is, it goes from 0 to n. The index on B goes from n to 0, but if you add these indices together, you get n. So Cn contains all products whose subscripts add up to n. Therefore, if I add up the C's from subscript 0 to n, that will contain all of the A times B's whose subscript is less than or equal to n, because it contains everything with subscripts adding up to 0, adding to 1, adding to 2, all the way up to subscripts adding to n. So this justifies why the sum of the Cn's contains all possible ai times bj, because whatever ai and bj you might pick, their subscripts add up to something and will therefore eventually be accounted for in here. Now, instead of letting epsilon be positive and picking an index, etc., we're going to consider a partial sum and compare it to AB and see what that difference is, and then see that we can make the difference arbitrarily small. So we're going to abbreviate some partial sums so that we don't have to keep writing the sigma over and over again with capital letters. So capital AM is a partial sum of little a's, capital B, capital C, partial sums of little b and little c. Okay, this proof is going to go on for a little bit, so let's see what's going on here. Let's take a look at this absolute value. Capital CM, as remarked, contains all products of little a times little b whose indices add up to less than or equal to m. Now let's look over here. Here I have a little a and a little b whose indices add up to exactly n. I goes from 0 to n allows this to account for everything where the sum is exactly n, but now n ranges from 0 to m. So this accounts for all little a little b whose subscripts add up to anything from 0 to m. That's exactly what capital C sub m was. Next, okay. Ignore this AB because we haven't changed it yet. Let's just look at this sum. Here, capital B sub n was little b 0 plus little b1 up to little b sub n. So now I have A with a subscript times B sub 0, but also times B sub 1, times also B sub 2, all the way up to B sub n. But this does stop at index little n, meaning this now accounts for all little a times little b, where the subscripts add up to, at most, capital M. And that goes as n goes from 0 to m. So we have accounted for all little a times little b, where they have indices that add up to, at most, m. That's exactly what we started with here. Now moving on to this term. Again, this minus AB hasn't changed yet, so don't worry about that. We're just comparing this parenthetical term to this plus that. Okay, note that this AM minus n hasn't changed. So what's going on here? We have Bn being replaced with Bn minus b. That's fairly straightforward. What happens when I take this minus b and I multiply it by this sum as n goes from 0 to m? Well, as n goes from 0 to m, I have little a with subscript m counting down to 0. But that's just capital AM. It's all of the little a's, a0 plus a1 up to am. So here I have a minus b times all those little a's, and here I have a plus b times all those little a's. So this absolute value is equal to this gigantic term here. Now let's apply an inequality. We're just doing a triangle inequality here in essence. Okay, so this term less than or equal to, putting the absolute values inside, and then I have this thing that I represent as a single term where I've factored out the capital B. So first step, triangle inequality, split this up into two terms. Then triangle inequality on this finite sum, move the absolute value inside, and on this term here, factor out the B. So here's where we were at the end of the previous slide. Now this second term, this thing over here, remember that capital A sub m is a partial sum of this series, which is converging to capital A. So if little m is very big, I can make this as small as I want. And since capital B is just a constant, by making little m as big as I want, I can make this as small as I want. The first term takes a bit more work. Okay, so we're just going to focus on making this term small. Observe that b sub n does converge to b. So as n gets big, I can make this big, but observe that n goes from 0 to m. So n can't just be big. I still have to account for small terms here. But when little n is large, this is small. But the sum of an converges. One of our running hypotheses was that this was a converging series, which means the underlying sequence of a's goes to 0. So when n is big, this is small. But when n is small, this index is big, which means this absolute value is small. So just looking at that first term, let's be a little more specific. Pick epsilon to be positive. We know that because the sum of the a's converges to capital A, and remember this is the partial sum of this converging series, and this is a partial sum of this converging series, so I can make both of these less than epsilon if m is sufficiently big. But the a's aren't just converging, they're converging absolutely, which means that the sum of absolute values converges, so its tails can be made arbitrarily small, so partial sums from its tail can be made arbitrarily small. So I can pick capital K so that the tail of the absolutely convergent series is also less than epsilon, meaning any of its partial sums is still less than epsilon. Now this series of b's is converging. Perhaps not absolutely, but it is converging. So this limit is definitely 0. So I'm going to pick capital B max to be the supremum of all of these distances. Because this is a sequence converging to 0, it is bounded, so it has a supremum. All right, so we took B max to be this supremum. Now we're going to take little m to be bigger than or equal to 2k. Specifically, m plus 1 is bigger than 2k, or m plus 1 minus k is bigger than k. Now let's take a look at this thing we needed to estimate. First, instead of summing from 0 to m, sum from 0 to m minus k, and then account for the rest of the terms here. Now, in the first term, I have this absolute value of bn minus b, starting at index 0 and stopping at a certain point. Every single one of these is no larger than b max. So replace all of these with b max. Now look what you have here. That's just a constant, factor it out. This is little a, m minus n. N goes from 0 to this, so m minus n will start at capital M and then count down until you pick n equals to m minus k, and you'll get exactly k. So this goes from a sub m counting down to a sub k, which we write in this order, going from a sub k up to a sub m. In this second term, we also had that this, for large indices, was less than epsilon. So replace that with an epsilon, and again, as n goes from this value to this one, a sub m minus n accounts for indices 0 to k minus 1. So the less than or equal comes from replacing this with B max and this with epsilon. So here's where we are now. The thing we need to estimate is less than or equal to the sum of these two terms. I can factor this epsilon out and be left with just this sum of the absolute value of ANs, but also this is a piece of a tail from our absolutely convergent series, which I also assumed was less than epsilon for sufficiently large indices. Factor that out. So now the thing we needed to estimate is less than or equal to epsilon times a fixed constant times a partial sum of an absolutely convergent series, which means the thing we needed to estimate is no larger than epsilon times a constant plus the value of capital A. So introducing this term back into where we started with all of this, we get this epsilon times B max plus this sum plus this term over here. Because A sub m can be made close to capital A, I can turn that into another epsilon and factor it out. So here's where we are. Now I set A star to be whatever the value of this absolutely convergent series is. This is a partial sum of an absolutely convergent series. It's less than or equal to the value of the absolutely convergent series. And now we see that that term in parenthesis is a finite constant. So I can make the thing an absolute value as small as desired. I can make it arbitrarily small. And the proof is finally done. I can make the partial sum of the C's minus AB as small as necessary for large enough m. That is to say, the sum of the C's converges to AB. Okay, given the two series AN and BN in Mertens theorem, we constructed this, the sum of Cn. This is called the Cauchy product of the two original series, and Mertens theorem says the Cauchy product converges provided both series converge and one of them converged absolutely. But we required one of the series to converge absolutely. If they both converge conditionally, the Cauchy product doesn't have to converge at all. So for our example, AN and BN will be the same conditionally convergent series, alternating 1 over root n, with a plus 1 in there because we want to start at index 0. So what happens when you compute Cn? You need to take this AI times Bn minus I. So here's AI, here's Bn minus I. What happens in the numerator? You get exactly -1 to the n. But that's a constant as far as this sum is concerned. It doesn't have an I in it. So the -1 to the n can factor out. So when you take an absolute value, it doesn't matter whether it was +1 or -1. And your denominator is just this radical. Okay, so here's what we have. Now let's look at a quadratic function. Super complicated, I know. X plus 1 times n minus x plus 1. N is just some fixed number here. What are the roots of this quadratic? X equals -1 or x equals 1 plus n. So where's the vertex? At the midpoint, which is exactly n over 2. Also, if you expand out that quadratic, it has a negative leading coefficient. So it's a downward opening quadratic with a vertex at n over 2. So the value of the quadratic is less than or equal to the value at the vertex. And if you simply plug in n over 2 and compute what's going on here, n minus n over 2 is another n over 2. You get n over 2 plus 1 squared. So the thing under the radical is less than or equal to n over 2 plus 1 squared. So 1 over the thing in the radical is bigger than or equal to 1 over the square root of n over 2 plus 1 squared. The square root and the square cancel out because we have no negative numbers here, not a problem. And now this summand, 1 over n over 2 plus 1, does not involve the index of summation. It's effectively a constant. How many terms are there in this sum? N plus 1 of them. So we get n plus 1 times the constant 1 over n over 2 plus 1. So we've just established that the absolute value of Cn is at least as big as n plus 1 over n over 2 plus 1. It's pretty quick to verify that the right side does not converge to 0. Therefore, the absolute value of Cn does not converge to 0, so the sum of the Cn's doesn't converge. So that Cauchy product didn't converge at all. Moving on to a more important, useful topic, power series. Fix any real number you want. By definition, a power series about x0 is a series of the following form. So a power series is now a function of x. Depending on the value of x, this series may or may not converge. Many important functions are written as power series. For the specific case where x equals x0, so you get a 0 here, and n equals 0, you take the convention that 0 to the 0 when writing power series is just taken to be 1. Technically it's indeterminate, but when you are writing power series, everyone understands that when x equals x0 and n equals 0, you intend for that to be 1. A power series is said to be convergent if there is at least one value of x other than x0 for which the series converges. If x equals x0, you are guaranteed convergence. If x equals x0 and n is positive, all of these are 0. So all terms except the first are 0, you definitely get convergence of the series in that case. If the series only converges when x equals x0 and does not converge anywhere else, you say the series is divergent. Let's take a look at an example. Consider the power series x to the n over n factorial. Let's apply the ratio test to see whether or not this series converges. So we compute the limit of the absolute value of the next term over the one before it. A whole bunch of stuff cancels out, and you are left with the limit as n goes to infinity of x over n plus 1. But now that x is a constant, and we're taking a limit as n goes to infinity, and we're dividing by n plus 1. It doesn't matter what x is, you end up with a 0 here. Therefore, the series converges absolutely, and x didn't really matter. So for every value of x, this series converges absolutely. Another example, let's take the power series x to the n, not over n factorial, just over n. Now we'll use the ratio test, and we end up with the x to the n plus 1 over x to the n simplifies as x in absolute value. It's a constant, factor it out, but now you have a limit of n over n plus 1, which is 1. So when you apply the ratio test, you end up with this constant absolute value of x, whatever it is. That converges by the ratio test, absolutely, as long as x is in between plus or minus 1, and it diverges, again by the ratio test, if the absolute value of x is larger than 1. Then you can ask, I know convergence between minus 1 and 1. To the right of 1 and the left of 1, I know I have divergence. What about the specific values of plus or minus 1? When the absolute value of x is equal to 1, well, if x equals 1, 1 to the n is just 1, and you get the harmonic series, which diverges. When x is equal to minus 1, you get the alternating harmonic series, which converges. So at one of those values it diverged, and at the other it converged. So where does this series converge? Everywhere in between plus or minus 1. It also converges at minus 1, but not at plus 1. And it diverges when the absolute value of x is larger than 1. Another example, consider this power series nx all raised to the n. Let's apply the root test. We take the absolute value of the general term to the 1 over n, the nth power and the 1 over n cancel out. What's the limit as n goes to infinity of n times x in absolute value? Well, if x is 0, you just get 0 here as a constant. But if x is anything other than 0, the absolute value of x is a positive number, and I multiply it by n as n goes to infinity, that goes to infinity. So the only value of x for which this series can converge by the root test is 0. For every other value of x, it diverges by the root test. So let's talk about that. The previous examples show in general what power series can do. They might converge everywhere. They might converge on a specific interval and diverge out that interval, or they might diverge everywhere. So now we'll prove a result that sort of states that concretely. So prop 2.6.10, suppose you have a power series. Either the series converges only for x equals x0, or it converges everywhere, or there is some positive number rho so that the series converges absolutely when x minus x0 is less than rho in absolute value, diverges when it's bigger than rho, with no concrete claim made when you get exactly equal to rho. Let's prove it. Okay, denote by r the lim sup as n goes to infinity of the absolute value of an to the 1 over n. Then we're just going to apply the root test. The reason being that this x minus x naught to the n is going to interact very nicely with the root test. So we take the lim sup of the general term to the 1 over n. This x minus x naught to the n to the 1 over n is just a constant x minus x naught in absolute value, and we denoted this lim sup to be r. If r is plus infinity, then for any value of x other than x naught, you get this lim sup to be plus infinity, so by the root test, the series diverges. If r is equal to 0, it actually doesn't matter what x is. By the root test, the series converges. However, if r is anything in between 0 and infinity, then you simply set rho equal to 1 over r, and the root test will tell you the series converges absolutely when you have the absolute value of x minus x naught less than rho, because then this would be less than 1. Diverges when this is bigger than 1, in other words, when x minus x naught in absolute value is larger than rho, with nothing determinate stated when x minus x naught in absolute value equals 1 over rho, in other words, when this lim sup is equal to 1. So the quantity rho, or 1 over r, in other words, 1 over the lim sup, as n goes to infinity of the absolute value of an to the 1 over n, is called the radius of convergence of the original power series. So here we understand that if r, this lim sup, is equal to infinity, we set rho equal to 0, and similarly, if capital R is equal to 0, we kind of declare 1 over that to be plus infinity. So the fact that power series converge absolutely when the distance from x to x naught is less than rho leads to an immediate result, the proof of which we omit. So the following is more or less immediate. Suppose an and bn are coefficients of two different power series. Assume they both have a radius of convergence at least as large as rho. Let alpha be an arbitrary real number. Then as long as the distance of x to x naught is less than rho, in other words, it's within the radius of convergence of both power series, and form coefficients Cn as stated here, the sum of the two power series forms a convergent power series. Alpha times a convergent power series forms a convergent power series, and the product is again convergent where the new coefficients are given through these Cauchy products. So for all x within rho of x naught, we now have two convergent series. The term-by-term addition and multiplication is quite direct. Now for such x's, the series converges absolutely. If we're within the radius of convergence, we converge absolutely. Therefore, we can apply Mertens' theorem to find out what happens to the product of the two series. So after performing these algebraic operations, if you have two different power series whose radius of convergence is at least as large as rho, the sum and product also has radius of convergence at least as large as rho. It's worth stating the radius of convergence of the result can be strictly larger than either of the series we started with. There are exercises to this effect. Let's talk about power series and polynomials. Polynomials are just finite power series. So the ANs, in other words, those coefficients, are 0 for all n large enough. If we expand a polynomial as a power series about any point, we can do that by doing a bunch of tedious work by making terms x minus x naught to the n. So for example, 2x squared minus 3x plus 4. If I want this to be in terms of x minus 1, you can verify that 2x squared minus 3x plus 4 is 3, 1 times x minus 1, and 2 times x minus 1 squared. You can also expand rational functions as power series. Okay, we're not going to completely prove that here. But notice that a series for a rational function only defines the function in the radius of convergence. In other words, on a specific interval, even if the function is defined elsewhere. For example, for the geometric series, we had 1 over 1 minus x is the sum of x to the n. This is a power series equal to that. But this only converged for x in between plus or minus 1, whereas this is defined for all x other than 1 itself. So this power series equals this function on an interval, specifically the interval of convergence for the power series. Now you can use the geometric series, together with various rules for addition and multiplication, to expand rational functions as power series as long as the denominator isn't 0 at x naught. So again, we're going to state this without proof. This is always possible, and the radius of convergence will be exactly as big as it could be. So wherever you are deciding to center your power series, your choice of x naught, if p is the nearest root of the denominator, the distance from where you are trying to center to that nearest root will be exactly the radius of convergence. But next we're going to give an example of a computation like this using the geometric series. So example 2.6.13, consider the rational function x over 1 plus 2x plus x squared. We'll write it as a power series centered around the choice of x naught equals 0 and find the radius of convergence. Step 1, factor the x from the numerator out, observing that 1 plus 2x plus x squared is simply 1 plus x squared, and rewrite 1 plus x as 1 minus minus x. Why? Because 1 over 1 minus r is the geometric series, the sum of r to the n. So we're simply choosing r to be negative x. Negative x to the n, negative 1 to the n times x to the n. Now we're going to apply Mertens' theorem. I have a power series squared. That's a product of two convergent power series. We can write it as a single power series where the coefficients are given by these Cauchy products Cn. Why? Because now I can distribute this x in. That was really why we wanted to apply Mertens' theorem. Rather than two power series floating around here, I just have one, distribute the x inside, and re-index. So now we simply have the sum, n goes from 1 to infinity, c sub n minus 1, x to the n. It's quite typical, it's almost mandatory in power series that your exponent on the variable x should equal the index of summation. So in this line here, where we had an n plus 1 as our exponent, we wish to re-index that to just get an n. So we've expressed our rational function as this power series. Now those Cn's were Cauchy products, and remembering back to our expression on the previous page, all of our coefficients were merely powers of minus 1. Cn is the sum as I goes from 0 to n, negative 1 to the I, negative 1 to the n minus I. These multiply together to simply be negative 1 to the n, a constant as far as this sum is concerned. There are n plus 1 terms in the sum, giving us this expression right here. Observe in our power series, the index on C is reduced by 1. So when n is 1, C0. C0 is 1 times negative 1 to the 0. When n is 2, we get C1. C1 is 2 times negative 1 squared. So you end up with x minus 2x squared plus 3x cubed minus 4x to the fourth and so forth. And as an exercise, the radius of convergence is exactly 1. This isn't terribly difficult. I would just apply the ratio test or the root test for that matter. Okay, a quick word about partial fraction decompositions. Recalling back to basic calculus, any rational function may be decomposed as a sum of a bunch of functions of the following form, a polynomial plus, something like this. So if we may determine power series for either a over x minus r or a linear function over an irreducible quadratic, we can apply Mertens' theorem to find power series for these things here, then add them all together and get a power series for an arbitrary rational function. I'm not saying it isn't tedious, but it's doable. Okay, the first term is a geometric series. This isn't bad. The second one is going to be left as an exercise, right? This is just a geometric series. This is a bit worse, but doable. So let's review everything from this section. We did a whole bunch more content on convergence of series. Specifically, we introduced and proved the root test and alternating series test. Most people at this point have seen these tests before. Now we're just working through the formal proofs. Riemann's rearrangement theorem and Mertens' theorem are less familiar to students, but they're somewhat interesting to have. Riemann's rearrangement theorem is a nice abstract result about a crucial distinction between absolutely convergent and conditionally convergent series and how they interact with rearrangements. Mertens' theorem is a bit more technical, has a lot more to do with determining the coefficients of a power series when you multiply two other power series together, provided at least one of them was absolutely convergent. Okay, we also introduced power series for that matter, which will be very important for us later, for example, when we discuss Taylor's theorem.